There's a moon in our solar system hiding an ocean 3 times bigger than every drop of water on Earth, and we've never once touched it. It's been waiting there for billions of years in complete darkness under miles of ice, and something down there might be alive. Today, we go to the most terrifying moon in the solar system. This is Europa. Now let's begin. Europa contains more liquid water than all of Earth combined, not twice as much, not 1.5 times. Between 2 and 3 times the total volume of every ocean, every lake, every river, every glacier, and every drop of groundwater on our entire planet. And it sits inside a moon that is only about 10% smaller than our own moon orbiting, a gas giant more than 600 million kilometers away. From where you are standing right now, listen that again, a moon, not a planet, a moon. Take a moment to feel the weight of that number. Earth has approximately 1.34 billion cubic kilometers of water. It covers 71% of our planet's surface. It is the defining feature of our world, the reason life exists here, the reason explorers crossed it for centuries in wooden boats. And Europa, a frozen airless ball of ice and rock in the outer solar system, holds more of it than we do, possibly 3 times more. That number alone should stop you cold, but it only gets stranger from there. The surface temperature on Europa sits at around negative 160 degrees Celsius. To put that in terms your body can grasp, that is cold enough to freeze carbon dioxide into dry ice. At negative 78 degrees Celsius, carbon dioxide solidifies. Europa's surface is more than 80 degrees colder than that. If you placed a block of dry ice on Europa's surface, it would not sublimate. It would simply sit there, frozen solid. Because the ambient temperature is already far too low for it to behave the way dry ice behaves on Earth. Metal becomes brittle at those temperatures. Rubber shatters like glass. The human body would freeze through in seconds. And yet, according to NASA's estimates based on decades of observational data, somewhere beneath that, killing cold beneath a shell of ice that has no business sitting above liquid water, there is an ocean. A real ocean. Liquid water, not frozen, not vapor liquid. Estimated to be somewhere between 60 and 150 kilometers deep. To understand how extraordinary that depth is, consider this: the deepest point on Earth is the Challenger, deep in the Mariana Trench, sitting at approximately 11 kilometers below sea level. That is the absolute bottom of everything we have explored on our own planet, the place where pressure crushes steel and no sunlight has ever reached. Europa's ocean, at its conservative estimate of 60 kilometers, is more than 5 times deeper than that. At its upper estimate of 150 kilometers, it is nearly 14 times deeper than the deepest point on Earth. Think about what that means in terms of sheer volume of water. An ocean more than 100 kilometers deep, wrapping entirely around a world roughly 3,000 kilometers across. The numbers become almost too large to hold in the mind. Here is a comparison that might help. Imagine Europa as a hard-boiled egg. The shell, hard, cold, lifeless on the outside, is the ice crust. Crack through that shell and instead of solid white, you find something still liquid, still warm, still moving. The yolk at the center is the rocky core, but the space between the shell and the yolk, that fluid interior, is not protein and fat. It is an ocean that dwarfs every body of water on Earth. And unlike an egg, that yolk, that core, might be generating enough heat to keep everything above it from freezing. Now ask yourself a serious question. If there is a massive ocean locked under ice for potentially billions of years, completely cut off from sunlight, completely isolated from the surface, what could possibly survive in there? Not what could theoretically survive in some abstract, hypothetical sense. What could actually, right now at this moment as you read these words, be alive in that darkness? That question is not science fiction. It is the question that has driven some of the most expensive, most carefully designed space missions in human history. It is the question that kept scientists awake after the data from the Galileo spacecraft came back in the 1990s. It is the question that NASA spent $5 billion trying to answer when it launched the Europa Clipper in October of 2024. Europa is not a planet. It is not even the largest moon in the solar system. That title belongs to Ganymede, also orbiting Jupiter. Europa is the 6th moon outward from Jupiter, roughly the size of our moon, and for most of human history, it was nothing more than a point of light in the telescope of Galileo Galilei, a dot, a curiosity. But beneath that dot, beneath that frozen shell drifting through the void more than 600 million kilometers from Earth, there may be more water than anywhere else in the known solar system, and somewhere in that water, in that darkness, in that crushing pressure and absolute cold, something may be alive right now. That is what makes Europa the most terrifying moon in the solar system. Not because it is violent, not because it would kill you instantly if you stood on its surface, but because it might not be empty, because the most important discovery in human history, confirmation that life exists beyond Earth, might already be waiting right now in an ocean we have never seen, on a world we have barely begun to understand. But before understanding why Europa is as terrifying as it is necessary to understand how it came to be, what it is, and why Jupiter itself is the very thing keeping Europa alive. In the winter of 1610, Galileo Galilei pointed a telescope at Jupiter and noticed something unusual. There were 4 small points of light clustered near the planet, and night after night they moved. Not randomly, they shifted positions in a way that could only be explained if they were orbiting Jupiter itself. Those 4 points of light were Io, Europa, Ganymede, and Callisto, and their discovery cracked open the entire foundation of how humanity understood the universe. Before 1610, the dominant model of the cosmos was geocentric, Earth at the centre, everything else revolving around it. The moon orbited Earth, the sun orbited Earth, the planets orbited Earth. This was not merely scientific consensus, it was theological doctrine, philosophical certainty, the organising principle of the civilized world. Then, Galileo watched 4 tiny moons circling Jupiter, and the argument collapsed. Here were 4 celestial bodies that demonstrably did not orbit Earth. The cosmos was not built around us. We were just one object among many in a system that operated by the same gravitational rules everywhere. It was the first time in recorded human history that anyone had observed a body in space orbiting something other than Earth. And one of those 4 bodies was Europa. For roughly 3.5 centuries after that discovery, Europa remained exactly what Galileo saw, a dot, a name on a list of Jovian moons. It was not until the Voyager spacecraft flew through the Jovian system in 1979 that humanity got its first real look at Europa's surface, and what Voyager saw was deeply strange. Instead of the cratered, battered face expected of an old moon, Europa's surface was almost smooth, covered in a web of dark reddish-brown lines running in every direction like cracks across the surface of a broken eggshell. Europa is approximately 3,100 kilometers in diameter, making it about 10% smaller than Earth's moon, but it is noticeably denser, suggesting a composition that includes significantly more rock and metal relative to its size. It sits at an average distance of roughly 670,000 kilometers from Jupiter, making it the second of the 4 Galilean moons outward from the planet, orbiting Jupiter once every 3.5 Earth days. That proximity to Jupiter is not a minor detail. It is the entire reason Europa is the world it is. Europa's interior is structured in distinct layers moving from the outside inward. The outermost layer is the ice shell, estimated based on current models to be somewhere between 10 and 30 kilometers thick. Below that ice shell, the models predict an ocean of liquid water estimated between 60 and 150 kilometers deep. Below the ocean lies a layer of rock, and at the very core, likely metal. If Earth were imagined as a 100-story building, Europa's ocean would be equivalent to 50 floors of pure water sitting in the middle, sandwiched between ice above and rock below. A vast interior sea wrapped entirely around the moon, hidden from the universe by a ceiling of ice. When you look at images of Europa's surface, the first thing that registers is the colour. It is not the grey-white of Earth's moon or the rust-red of Mars. Europa's surface is pale and bright at its base, but streaked and stained with patches of yellow-brown and reddish-orange that bleed outward from the systems of cracks like old bruises beneath skin. Scientists have identified these discolorations as salts and sulfur compounds, materials that have migrated upward from beneath the surface and been chemically altered by the intense radiation bombardment coming from Jupiter. Europa is in a very literal sense sweating chemicals up through its ice, leaving stains across its own face. That detail points towards something important. The surface is not sealed. Material from below is finding its way up. The ice is not a perfect barrier between the interior and the exterior. It is a dynamic, active boundary. and what lies beneath it is influencing what is visible from space. But the most revealing thing about Europa's surface is what is not there. Most solid bodies in the solar system are covered in impact craters, the accumulated scars of billions of years of collisions with asteroids and comets. Our moon is covered in them, Mars is covered in them, Mercury is covered in them. Craters are the geological record of time, each one a timestamp pressed into the rock. A heavily cratered surface is an old surface, one that has been sitting exposed and unchanged for hundreds of millions or billions of years. Europa has almost no craters. Its surface is extraordinarily smooth by the standards of solar system bodies. The craters that do exist are shallow and deformed, as though the ground beneath them was soft when they formed and slowly absorbed the impact over time. Current estimates place the age of Europa's present surface at somewhere between 40 and 90 million years. In geological terms, that is extraordinarily young. The solar system itself is approximately 4.5 billion years old. Europa as a moon is approximately 4.5 billion years old, but the surface you would be standing on if you were there right now formed less than 100 million years ago, roughly the same era when non-avian dinosaurs were going extinct on Earth. Something beneath Europa's surface has been continuously replacing it. The old surface, whatever it looked like, has been destroyed and rebuilt. The ice has cracked, shifted, refrozen, and renewed itself again and again over geological time, erasing the crater record and presenting a fresh face to the universe every few tens of millions of years. Something below is pushing up. Something below is generating enough energy to keep this process running for billions of years on a moon more than 600 million kilometers from the Sun, with no sunlight reaching its interior in a part of the solar system, where everything else is frozen solid. But what creates the heat that maintains that ocean? The answer is a mechanism that is simultaneously beautiful and brutal to a degree that is almost impossible to believe. Jupiter is the largest planet in the solar system, containing more mass than all other planets combined. More than 1,300 Earths could fit inside its volume. At that scale, gravity does not simply pull, it distorts. It reaches out across hundreds of thousands of kilometers and physically deforms everything near it, stretching and compressing solid rock and ice the way human fingers work a lump of dough. And Europa, sitting just 670,000 kilometers from Jupiter's center, is directly inside that gravitational grip. This is the mechanism called tidal heating, and it is the reason Europa's ocean exists at all. Here is how it works at the most fundamental level. As Europa orbits Jupiter, Jupiter's gravitational pull is not perfectly uniform across Europa's entire body. The side of Europa facing Jupiter gets pulled more strongly than the side facing away. This difference in gravitational force, called a tidal force, physically stretches Europa along the axis, pointing toward Jupiter, while compressing it along the perpendicular axis. Europa is not a rigid, unchanging ball. It flexes. Its surface rises and falls by roughly 30 meters, the height of a 10-story building, over the course of each orbital period. Every 3.5 Earth days, Europa completes one orbit, and during that orbit, its entire body is squeezed and squeezed again by the most massive planet in the solar system. To understand what that does to the interior, try a simple physical experiment. Take a lump of clay and squeeze it repeatedly in your hand. After only a few minutes, the clay will be noticeably warmer. The mechanical energy of your grip is being converted into heat through internal friction, the molecules of the clay resisting the deformation and generating thermal energy as they do so. That is precisely what is happening inside Europa. Except instead of a human hand squeezing clay for a few minutes, it is Jupiter squeezing an entire moon continuously, without pause for 4.5 billion years. The friction generated inside Europa's rock and ice by this constant deformation produces heat. Not a trivial amount of heat. Enough heat distributed through Europa's interior to prevent its subsurface ocean from freezing solid, despite being located in a region of the solar system where the Sun delivers only about 1/25 of the solar energy it provides at Earth's distance. Sunlight barely reaches Jupiter's moons. It is not the energy source keeping Europa's ocean liquid. Tidal heating is. Europa is, in the most literal sense, a moon that Jupiter has been massaging continuously for 4.5 billion years. The squeezing has never stopped. The heat has never stopped. And the result, sitting beneath 30 kilometers of ice in complete darkness, is a warm, liquid global ocean. It may be the strangest heat therapy in the universe, but it works. But here is where the mechanism becomes even more elegant and even more locked in. Tidal heating only works at the scale it does on Europa because of a gravitational relationship between three moons that could not have been designed more precisely if someone had tried. Europa does not orbit Jupiter alone. It shares Jupiter's system with dozens of other moons, but three of them, Io, Europa and Ganymede, are locked into a gravitational relationship called orbital resonance. For every one complete orbit that Ganymede makes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. The ratio is 1 to 2 to 4, and it is not a coincidence. It is a stable gravitational configuration that the three moons have settled into over billions of years, and it is self-reinforcing. The gravitational interactions between the three moons continuously nudge each other back into this precise ratio whenever they drift away from it. This resonance has a critical consequence for Europa. For tidal heating to generate significant heat, the moon being squeezed needs to have an elliptical orbit, one that brings it closer to and then farther from Jupiter during each orbital period. If Europa's orbit were a perfect circle, the tidal force would be constant in magnitude, the moon would deform to a fixed shape and stay there, and almost no heat would be generated. Friction requires change. It requires the deformation to be constantly varying. The orbital resonance with Io and Ganymede continuously forces Europa's orbit to remain slightly elliptical. Every time Europa lines up with Io or Ganymede, their combined gravitational pull tugs Europa's orbit slightly out of round. Europa never settles into a circular path. The ellipticity is maintained, the variation in tidal force is maintained, and therefore the heating is maintained permanently for as long as the resonance holds. Io, sitting closer to Jupiter than Europa, and experiencing even more extreme tidal heating, is the most volcanically active body in the entire solar system. Its surface is covered in hundreds of active volcanoes constantly erupting sulfur and silicate material. Io is being torn apart by the same mechanism that heats Europa, just at greater intensity due to its closer proximity to Jupiter. Europa's version of this process is gentler instead of surface volcanism. The heat stays buried in the interior, warming the ocean from below. Estimates of the total thermal energy generated by tidal heating inside Europa suggest it is comparable to the combined output of hundreds of simultaneously active volcanoes. To put that in terms of sheer power, consider that a single major volcanic eruption on Earth, the kind that darkens skies and reshapes landscapes, releases energy equivalent to thousands of nuclear bombs. Europa, with no eruptions visible from the surface, with no smoke and no lava, is generating the thermal equivalent of hundreds of such volcanoes, continuously, silently, invisibly, driven entirely by the gravitational squeeze of a planet it has been orbiting since the solar system was young. That energy budget is sufficient to maintain a liquid ocean despite the absence of sunlight. It is sufficient to drive convection within the ocean, the movement of warmer water upward and cooler water downward, the same circulation that drives Earth's own ocean currents. It may be sufficient to drive hydrothermal activity at the ocean floor, where the water contacts the rocky interior, and heat is transferred directly from the rock into the water. So, there is a massive ocean warm, completely dark, that has existed for billions of years. The next question is, what does that ocean actually look like on the inside? Stand at the bottom of Europa's ice shell and look upward. You will see nothing. Not dim light filtered through kilometers of ice, not a faint glow from some distant source, nothing. Complete, total, absolute darkness. There is no sun visible from Europa's subsurface. There is no moon to reflect light into the ice. There is only water above water below water in every direction, and a darkness so complete and so permanent that no photon from any star has penetrated it in billions of years. This is Europa's ocean as it actually exists, not the romanticized version with shafts of blue light filtering down through crystal ice. The real version, a lightless, pressurized, kilometers-deep body of liquid water, wrapped entirely around a rocky world, isolated from the universe above it by a ceiling of ice, 30 kilometers thick. The pressure inside that ocean is one of the first things that makes it genuinely alien to anything in human experience. On Earth, the pressure at sea level is defined as 1 atmosphere, roughly 1 kilogram of force pressing down on every square centimeter of surface. At the deepest point in Earth's ocean, the Challenger Deep in the Mariana Trench pressure reaches approximately 1,000 atmospheres, That is the maximum pressure found in Earth's natural water environments. And it is already enough to implode unprotected submarines and crush the human body instantly. Europa's ocean is estimated to be between 60 and 150 kilometers deep. The pressure at the bottom of such an ocean would reach into the thousands of atmospheres, potentially several times greater than anything found in Earth's deepest trenches. At those pressures, water does not necessarily behave the way water behaves at the surface. Under sufficient pressure, even relatively warm water can be forced into a solid phase, not the ordinary ice that forms in a freezer, but a class of high-pressure ice phases with different molecular structures, sometimes called hot ice or superionic ice, depending on the temperature and pressure involved. It is a form of matter that does not exist naturally anywhere on Earth's surface, a state where water molecules are locked into a crystalline structure, while their hydrogen atoms flow freely through it like a liquid within a solid. This means the very bottom of Europa's ocean may not be liquid water contacting the rocky seafloor. It may be a layer of exotic high-pressure ice sitting between the liquid ocean above and the rock below, depending on the exact thermal and pressure conditions at depth. The interior of Europa may contain forms of matter that have no analogue in any environment human beings have ever explored. But here is where the potential for life enters the picture. Scientific models of Europa's interior suggest that, in at least some regions, the base of the ocean does make direct contact with the rocky seafloor, and that seafloor may not be geologically dead. If tidal heating is generating thermal energy throughout Europa's interior, some of that energy may be escaping through the rock at the ocean floor in the form of hydrothermal activity, HOT, chemically enriched water seeping up through cracks in the rock, heating the surrounding ocean, driving chemical reactions at the water-rock boundary. On Earth, this kind of environment was considered uninhabitable until 1977, when the deep-sea submersible Alvin descended to the floor of the Pacific Ocean near the Galapagos Rift and encountered something no one had predicted. Clustered around cracks in the sea floor where superheated water was venting into the cold ocean, there were entire ecosystems: shrimp, crabs, tube worms reaching 2 meters in length, their bodies swaying in the current of hot water rising from the vents, mats of bacteria covering every available surface, all of it living in complete darkness at crushing pressure in water laced with hydrogen sulfide, a chemical toxic to most surface life, with no access to sunlight and no connection to the photosynthetic food chains that support virtually every other ecosystem on Earth. These communities were surviving entirely on chemosynthesis, the process by which certain microorganisms extract energy from chemical reactions rather than from light. The vent water carried hydrogen sulfide and other reactive compounds up from the hot rock below, and bacteria oxidized those compounds to generate energy, forming the base of a food chain that supported complex multicellular life in an environment that had previously been assumed sterile. That discovery in 1977 permanently changed the definition of a habitable environment. Before the Galapagos Rift vents were found, the assumption was that all life ultimately depended on sunlight. After it became clear that sunlight was just one possible energy source, chemical energy from the interior of a planet could sustain entire ecosystems independently in complete darkness at extreme depths and pressures. If life on Earth can thrive in darkness, scalding heat and crushing pressure at the bottom of our oceans, why could Europa not? The chemical inventory of Europa's ocean, assembled from data collected by the Galileo spacecraft during its 11 flybys in the late 1990s, and supplemented by observations from the Hubble Space Telescope, is more favourable than might be expected from a frozen moon in the outer solar system. Instruments detected molecular oxygen, not bound up in minerals but free oxygen molecules in Europa's thin surface environment. They detected hydrogen peroxide on the surface. Produced by radiation breaking apart water molecules, they identified magnesium sulfate salts and sodium chloride, ordinary table salt consistent with a liquid water ocean that has been leaching minerals from rock over billions of years. Carbon dioxide has also been tentatively identified in more recent Hubble observations. Many of these compounds, oxygen, carbon, sulfur compounds, salts, are fundamental building blocks for the chemical reactions that support life as we know it on Earth. The ocean beneath Europa's ice is not a sterile pool of pure water. It is a chemically complex, energetically active environment that has been evolving in isolation for potentially billions of years, with heat from the interior minerals from the rock and a chemical toolkit that overlaps substantially with the conditions under which life first emerged on Earth. But could support life and actually contains life are two entirely different things. And this is where the story begins to get truly terrifying. Europa's surface is covered in thousands of kilometers of dark reddish-brown lines. They run in every direction, crossing, intersecting, curving, branching, some of them stretching continuously for thousands of kilometers across the ice wide enough that several kilometers of frozen terrain separate their edges. From orbit, they look exactly like the cracks on the surface of a hard-boiled egg that has been squeezed too tightly in a fist. A brittle outer shell fractured by pressure from within. The breaks spreading outward in long, branching patterns that record every stress the interior has ever exerted on the surface above it. These features are called lineae, the Latin plural of lineae meaning line, and they are among the most geologically informative structures ever observed on any body in the solar system. They are not decorative. They are not random. They are a written record inscribed directly into the ice of everything Europa's interior has been doing for tens of millions of years, and scientists have spent decades learning to read them. The lineae form through a process directly connected to tidal heating. As Jupiter's gravitational pull deforms Europa's body during each orbital period, the ice shell flexes. Sections of the shell that are under tension crack open, allowing warmer material from deeper in the ice, or in some cases liquid water from the ocean below, to well up into the gap and refreeze. The result is a double ridge. Two parallel walls of refrozen material rising several hundred meters above the surrounding surface with a trough running between them. Seen from above, these double ridges appear as dark lines because the material filling them contains the same salts and sulfur compounds that stain the rest of Europa's surface chemicals, dragged upward from the ocean, frozen into the B, cracks, and then darkened by radiation from Jupiter. But the lineae are not simply records of cracking. Some of them reveal something far more extraordinary. When researchers examined high-resolution images from the Galileo spacecraft, they noticed that certain lineae had been disrupted. The ice on either side of some fractures had shifted, rotated, translated, slid laterally so that the crack no longer aligned with itself. The terrain had moved. To understand what this meant, scientists did something that required patience and precision. They digitally cut out sections of Europa's ice shell that appeared to have shifted position and slid them back to where the lineae indicated they had originally been. Like reassembling a broken ceramic plate, they tried to reconstruct the original configuration of the surface. The pieces fit perfectly. The lineae on one displaced block of ice aligned exactly with the lineae on the adjacent block when the blocks were returned to their inferred original positions. The ice had not merely cracked, it had broken into distinct plates that had moved independently of one another, exactly the way tectonic plates move on Earth. Europa may be the only body in the solar system besides Earth where active plate tectonics is currently operating. A moon, 600 million kilometers away, locked under ice, may be running the same geological process that has built mountains, opened oceans, and driven the entire geological history of our own planet. If that is true, it carries an important implication for life. Plate tectonics on Earth does not merely rearrange the surface. It drives chemical cycling between the interior and the surface, recycling minerals and compounds that would otherwise become locked in the crust. If Europa's ice shell is doing something analogous, it may be actively exchanging material between the surface, where radiation from Jupiter is constantly producing oxidizing compounds like hydrogen peroxide and molecular oxygen, and the ocean below, where those oxidants could fuel chemical reactions that support life. Alongside the lineae, Europa's surface contains regions that look like nothing else in the solar system. These are called chaos terrain, and the name is apt. Across large patches of Europa's surface, the ice appears to have been completely broken apart, jumbled into irregular blocks and ridges, tilted at random angles, then refrozen in place. The chaos terrain regions look as though someone shattered. A frozen lake with a hammer stirred the fragments with a paddle, and then let everything freeze again before the pieces could settle back into any orderly arrangement. The most straightforward explanation for chaos terrain is that in those locations the ice shell thinned dramatically or melted through entirely, allowing liquid water from the ocean below to reach the surface or come very close to it. The ice broke up, floated as disconnected rafts on the liquid water beneath, drifted into new positions, and then refroze when the thermal conditions changed. The same thing happens in the Arctic Ocean on Earth when sea ice fractures and refreezes the resulting surface, has exactly the jumbled, chaotic appearance seen on Europa. The difference is that on Earth, the process is driven by seasonal temperature changes. On Europa, it may be driven by variations in tidal heating or local upwellings of warm water from the ocean floor. Episodes where the heat from below briefly overwhelms the stability of the ice above. If chaos terrain forms the way these models suggest, then at various points in Europa's history, and possibly at this moment, in certain locations, the ceiling separating the ocean from space has been thin enough to break. The interior has reached the surface. Whatever is in that ocean has at least temporarily come very close to the outside. And then in 2012 and again in 2016, the Hubble Space Telescope observed something that made that possibility suddenly viscerally concrete. Hubble's ultraviolet instruments detected what appeared to be enormous plumes of water vapor erupting from Europa's south polar region, rising 200 kilometers above the surface, more than 16 times the height of Mount Everest above sea level before dispersing into space. The features resembled the water plumes that the Cassini spacecraft had already confirmed on Enceladus, Saturn's moon, where geysers of ocean water are known to erupt continuously from fractures near the South Pole. If Europa's plumes are real and confirmed, they would represent the most direct possible evidence that the ocean exists, because the material in those plumes would have come from the interior of the moon, carried up through the ice and ejected into space. The implications of confirmed plumes are difficult to overstate. Drilling through 20 to 30 kilometers of ice to sample Europa's ocean directly is an engineering challenge that no current or near-future spacecraft is capable of meeting. It would require technology that does not yet exist, timelines measured in decades, and solutions to problems of communication and power that remain unsolved. But a plume requires no drilling. A spacecraft flying through a plume at carefully planned altitude would be passing through material that originated in the ocean itself. Water molecules dissolved, minerals, organic compounds, if any are present, potentially even microbial, cells, if life exists in that ocean. The ocean would be delivering its own samples directly into space, and a spacecraft would only need to be in the right place at the right time to collect them. This is the primary reason NASA's Europa Clipper mission was designed with the specific capability to detect and characterize plumes. Its instruments can measure the composition of gases and particles in Europa's thin surface environment, and if a plume is active during one of the spacecraft's 49 planned flybys, Clipper may be able to taste the ocean without ever touching the ice. If Europa's ocean is actively venting itself into space, if the boundary between that dark pressurized interior and the vacuum of the solar system is that permeable, then the question stops being theoretical. If the ocean of Europa is already pushing itself out into space, what is being carried out along with it? It is time to look directly at the evidence, and at the missions that have actually flown there to find the answer. The spacecraft that carried humanity's first real understanding of Europa was not built for Europa. When the Galileo mission launched from the Space Shuttle Atlantis in October 1989, its primary purpose was to study Jupiter, the planet itself, its atmosphere, its storms, its magnetosphere. Europa was one of 4 large moons on the itinerary scheduled for a series of close passes during the spacecraft's extended tour of the Jovian system. Nobody expected that a moon covered in cracked ice would become the most scientifically consequential target of the entire mission. Between 1995 and 2003, the Galileo spacecraft completed 11 dedicated flybys of Europa, approaching as close as 351 kilometers above the surface on its nearest pass. To put that distance in perspective, 351 kilometers is roughly the altitude at which the International Space Station orbits Earth. Galileo was skimming Europa at orbital altitude, close enough that its instruments could read the chemical fingerprints of the ice below and measure the local magnetic environment in detail that no telescope or distant observation could have provided. What those instruments found permanently changed the scientific consensus about what Europa is. The most important discovery came from Galileo's magnetometer, the instrument designed to measure magnetic fields. Jupiter itself generates one of the most powerful magnetic fields in the solar system, and that field extends far enough outward to envelop all 4 of its large moons. As Galileo flew through that field near Europa, the magnetometer detected something unexpected, a secondary magnetic field generated locally by Europa itself that was not constant. It fluctuated. It changed direction and strength in a pattern that was directly synchronized with Europa's orbital period. The Moon's own local magnetic signal varied in lockstep with how Europa moved through Jupiter's rotating magnetic environment. There is only one physical mechanism that can produce this specific pattern of fluctuation. A static magnetic field like the one generated by a solid iron core does not respond dynamically to changes in an external field, but a conductor does. When a conductive material is placed inside a changing magnetic field, electrical currents are induced in that conductor, and those currents generate their own magnetic field in response. The fluctuating local field that Galileo measured at Europa was the signature of electromagnetic induction, and the material generating it had to be a layer of electrically conductive material located close to Europa's surface. The conductivity required to produce the observed signal ruled out rock. It ruled out pure water ice. The only material consistent with the measurements was salt water, a liquid electrically conductive brine present in a continuous layer beneath Europa's ice shell, responding in real time to the fluctuations of Jupiter's magnetic field, the way a coil of wire responds to a changing current. This was the strongest indirect evidence ever obtained for a subsurface ocean on any world other than Earth. Galileo's spectrometer reinforced the conclusion from a different direction. When the instrument analyzed the composition of Europa's surface, it detected magnesium sulfate and sodium chloride compounds that on Earth are ordinary constituents of seawater. Magnesium sulfate is a soluble salt. Sodium chloride is table salt, the same compound that makes Earth's oceans taste the way they do. These materials were distributed across Europa's surface in patterns consistent with material that had been carried upward from below chemicals, dissolved in liquid water that had migrated through the ice frozen near the surface, then been exposed to Jupiter's radiation environment. The implication was clear. Whatever is beneath the ice contains dissolved salts, similar in character to the salts dissolved in Earth's oceans. The ocean below Europa, if it exists, is not pure water. It is chemically complex brine. There is a detail about the Galileo mission that deserves to be stated plainly because it is one of the stranger facts in the history of planetary science. The spacecraft completed 11 flybys of Europa and returned data that rewrote humanity's understanding of where liquid water can exist in the solar system, but it did all of this with a broken antenna. Galileo was equipped with a high-gain antenna designed to transmit data back to Earth at a rate of 134,000 bits per second. Shortly after launch, that antenna failed to deploy correctly. It never opened. For the entire mission, Galileo was forced to communicate through its low-gain backup antenna, transmitting at a rate of 160 bits per second. A standard text email of the kind sent millions of times per day in 1995 required approximately 40,000 bits. The spacecraft that discovered evidence for the most significant extraterrestrial ocean ever identified was operating at a transmission speed slower than the dial-up modems that consumers were using at the time to download images from early websites. The mission's engineers compensated through extraordinary data compression and careful prioritization of which observations to transmit first, but the fundamental constraint was inescapable. Humanity learned what it learned about Europa through a connection that would have been considered inadequate for sending a single photograph in the era before broadband internet. Despite that limitation, the mission continued operating for nearly 8 years. By 2003, the spacecraft had exhausted its fuel supply and its scientific usefulness, and mission controllers faced a decision. Galileo was going to fall somewhere. Left uncontrolled, its decaying orbit would eventually intersect with one of Jupiter's moons. The probability of it striking Europa was not negligible, and if it did, the consequences could be irreversible. Despite years of exposure to the vacuum of space and the intense radiation environment around Jupiter, Galileo carried microbial contamination. The sterilization techniques available in the 1980s were not sufficient to guarantee that every bacterial spore and every hardy microorganism had been eliminated from the spacecraft's surfaces and components. If Galileo impacted Europa and that contamination survived the impact, or if fragments of the spacecraft carrying biological material ended up in the ocean, the scientific integrity of any future search for life at Europa would be permanently compromised. it would become impossible to determine whether any biology detected in Europa's ocean was indigenous to Europa or had been delivered from Earth by a piece of hardware launched in 1989. NASA's planetary protection protocols existed precisely to prevent this scenario. On September 21, 2003, controllers sent a final command sequence to the Galileo spacecraft. The craft fired its engines one last time and plunged into Jupiter's atmosphere at a speed of approximately 50 kilometers per second, where it was destroyed by pressure and heat within seconds. The same spacecraft that had provided the most compelling evidence for Europa's ocean was deliberately sacrificed to protect that ocean from the possibility of contamination. Galileo opened the question, but to answer it, a completely different kind of mission was needed, and it has already been launched. On October 14, 2024, a SpaceX Falcon Heavy rocket lifted off from Launch Complex 39A at Kennedy Space Center in Florida, carrying the most sophisticated planetary science spacecraft NASA had ever built for a destination beyond Mars. The mission's name was Europa Clipper, and its target was a moon 600 million kilometers away that a spacecraft last visited more than 2 decades earlier. Europa Clipper is large by any standard used to measure interplanetary probes. When its solar panels are fully extended, the spacecraft spans approximately 30 meters from tip to tip, roughly the width of a basketball court. It had to be that large because of where it is going. Jupiter receives approximately 25 times less sunlight than Earth does, which means solar panels that would generate adequate power in Earth orbit must be dramatically scaled up to function at Jovian distances. The mission's total cost reached approximately $5 billion United States dollars, making it one of the most expensive planetary science missions in history, second only to the Mars Science Laboratory program and certain flagship Earth-observing satellites. The spacecraft will spend approximately 6 years in transit using gravitational assists from Mars and Earth to build up the velocity needed to reach Jupiter. Its projected arrival at the Jovian system is 2030, at which point it will not go into orbit around Europa. This is a deliberate design choice driven by the most hostile radiation environment in the solar system outside the Sun itself. Jupiter's magnetic field traps high-energy charged particles in radiation belts that surround the planet and extend outward through the orbits of its inner moons. Europa orbits directly inside these belts. The radiation flux at Europa's distance from Jupiter is intense enough to damage or destroy unshielded electronic components within weeks of continuous exposure. A spacecraft placed in orbit around Europa would accumulate fatal radiation doses too quickly to complete its scientific objectives. Instead, Clipper will orbit Jupiter itself at a safer distance from the worst of the radiation and make 49 carefully planned close passes by Europa over the course of its primary mission, dipping in close gathering data rapidly, and then retreating back to a safer orbital altitude before the radiation can cause significant damage. On its closest approach, the spacecraft will pass within approximately 25 kilometers of Europa's surface. The scientific payload carried aboard Clipper represents nearly every relevant measurement technique available to 21st century planetary science. A thermal emission imaging system will map surface temperatures, identifying locations where heat is rising from below. A near-infrared spectrometer will analyze the chemical composition of surface materials, building on Galileo's earlier detection of salts and sulfur compounds with far higher resolution. An ultraviolet spectrometer will search for the presence and composition of any atmospheric gases, including water vapor from potential plumes. A magnetometer will measure Europa's magnetic environment with precision orders of magnitude beyond what Galileo could achieve, providing new constraints on the ocean's depth, salinity, and conductivity. Most critically for the question of the ocean's structure, Clipper carries an ice-penetrating radar instrument designated Reason radar for Europa assessment and sounding ocean to near surface. Reason transmits radio waves that pass through the ice shell and reflect back from layers of different densities below. The instrument is designed to image internal structure through approximately 30 kilometers of ice, potentially enough to map the boundary between the base of the ice shell and the top of the liquid ocean below it. If that boundary can be directly imaged, it would convert the ocean from an inference based on magnetic measurements into a directly observed physical feature. And then, there is the possibility of the plumes. If one of Clipper's 49 flybys coincides with an active plume event with an eruption of water vapor rising 200 kilometers above Europa's south polar region, like the ones Hubble appeared to detect in 2012 and 2016, then the spacecraft's mass spectrometer and plasma instruments will be able to analyze the composition of that material directly. The mass spectrometer can identify individual molecules in the gas and dust passing through the instrument. If the plume contains amino acids, the chemical precursors to proteins, the instrument will detect them. If it contains complex organic molecules that form only through biological or prebiotic chemistry, the instrument will detect them. If it contains microbial cells, if there is life in Europa's ocean, and that life is being carried upward through fractures in the ice and ejected into space, then Clipper, flying through that plume at the right moment, will be passing through material that has come directly from the interior of another living world. Consider what that would mean. An amino acid detected in a plume above Europa would not by itself confirm the presence of life. Amino acids form through purely chemical processes, and they have been found in meteorites throughout the solar system. But a sufficiently complex and specific suite of organic compounds in the right ratios with the right structural characteristics would be a signature that chemistry alone struggles to produce. Biology generates patterns. Life concentrates certain molecules, excludes others, and creates combinations that are statistically improbable without biological catalysis. If Clipper's instruments detect those patterns in a plume from Europa's ocean, the conversation changes in ways that no subsequent revision could fully undo. What Clipper cannot do is equally important to state. It cannot land. It cannot drill. It cannot descend through the ice and look directly at whatever is swimming or crawling or photosynthesizing or not in the ocean below. Every measurement it makes will be remote radar returns from below the ice surface. Magnetic field variations interpreted through models of internal structure. Chemical signals detected in a thin haze of gas above the moon's surf ice. Clipper is the most capable reconnaissance mission ever sent to another world's ocean. It is not an ocean explorer. It is an observer, stationed at the edge of the most important body of water humanity has ever had reason to investigate. Equipped with the best instruments available for reading signals that pass through 30 kilometers of ice and 600 million kilometers of space before reaching a receiver on Earth. It is the most important reconnaissance in the history of planetary science. But even if Clipper finds every signal it was designed to find, what does it actually take to get down there, and what might be waiting underneath? Nobody knows exactly how thick Europa's ice shell is. That sentence stated plainly captures one of the more uncomfortable realities of planetary science at the edge of the solar system, that the most consequential boundary in the search for extraterrestrial life remains for now unmeasured with any precision. Current estimates place the thickness somewhere between 10 and 30 kilometers a range, so wide it reflects genuine scientific uncertainty rather than a matter of rounding. The difference between 10 kilometers of ice and 30 kilometers of ice is not merely a matter of degree. It is the difference between an engineering challenge that might be addressed within this century and one that may exceed the capabilities of any technology humans can currently imagine deploying. To understand what those numbers mean in practical terms, consider the thickest ice on Earth. At its maximum, the Antarctic ice sheet reaches a depth of approximately 4.7 kilometers, less than half the lower bound of Europa's estimated ice shell, and less than 1/6 of its upper bound. Drilling through the Antarctic ice sheet to reach the liquid water of Lake Vostok beneath it has occupied teams of Russian, American, and European scientists for decades. The first Russian drill reached the lake's surface in 2012, after more than 30 years of effort using equipment that had to be specially designed, transported to one of the most hostile and remote environments on Earth, and operated under conditions that regularly threatened both the machinery and the people running it. The result was access to a body of water approximately the size of Lake Ontario, sitting beneath ice that is less than 5 kilometers thick. Europa's ice, by the most optimistic estimate, is twice as thick. By the most pessimistic, it is more than 6 times as thick. The engineering concept that has received the most serious attention for eventually penetrating that barrier is called a cryobot, a robotic probe designed to melt its way downward through the ice rather than drilling mechanically through it. The basic principle is straightforward: a cylindrical vehicle heated from within by a nuclear power source, typically a radioisotope thermoelectric generator, of the kind that already powers several deep space missions, would press against the ice below it, melt a column of water, descend through that column, and allow the water above it to refreeze, sealing the passage behind it. The probe would carry scientific instruments designed to analyze the ice and water as it passes through them, and eventually to operate in the ocean itself once it breaks through the base of the shell. The concept is elegant in principle. In practice, it generates engineering problems of a kind that have no solved precedents. The most immediate is communication. As a cryobot descends through 30 kilometers of solid ice, how does it transmit data back to the surface? And how does the surface transmit commands back to it? Radio waves do not penetrate ice effectively at depth. Fiber optic cable trailing behind the probe is one proposed solution. But 30 kilometers of cable wound onto a spool small enough to fit inside a probe that must itself fit inside a spacecraft launched from Earth introduces mechanical complications that engineers have not yet resolved. Acoustic signaling through the ice is another candidate, but it is slower and carries far less data. The communication problem is not a detail to be worked out later. It is a fundamental constraint that shapes every other aspect of the design. Then there is the question of time. Even under optimistic assumptions about the technology and the ice thickness, a cryobot melting its way through Europa's shell would require years to reach the ocean. Some estimates suggest the transit time could extend to a decade or more, depending on the ice properties, the probe's power output, and conditions encountered along the way. The probe's power system must operate reliably for that entire period without maintenance or repair. Its instruments must survive the journey. Its communication systems must function continuously. All of this must happen in an environment of intense radiation mechanical stress from the refreezing ice and temperatures that vary enormously between the surface and the subsurface. Engineering for reliability over a decade-long journey through the interior of another world's ice shell with no possibility of intervention if something goes wrong represents a category of challenge that no space agency has yet had to solve. But the engineering problems, formidable as they are not the most profound obstacle to sending a cryobot to Europa. The most profound obstacle is biological. If Europa has life, if there is anything living in that dark ocean from single-celled organisms metabolizing hydrogen sulfide around hydrothermal vents, to something more complex, drifting in the cold water above them, then the arrival of a probe carrying bacteria from Earth would constitute a catastrophic contamination event. Earth's biosphere is extraordinarily rich in microbial life. Surfaces that appear clean to human senses carry billions of microorganisms per square meter. Even spacecraft that have been carefully cleaned before launch carry thousands of bacterial spores per square meter on their exterior surfaces, resistant to heat and radiation, and vacuum, capable of surviving the interplanetary journey in a reminds state of suspended animation. If those organisms were introduced into Europa's ocean, they could outcompete, overwhelm, or simply confuse any attempt to detect life that was already there. The scientific mission, the entire purpose of the journey, would be destroyed before it had properly begun. Worse, if Europan life exists and is vulnerable to terrestrial pathogens, the contamination could cause damage whose extent cannot be predicted or reversed. NASA's planetary protection protocols address exactly this problem, and they do so with a seriousness that reflects how thoroughly mission designers have thought through the consequences of getting it wrong. Any spacecraft designated for contact with Europa's ocean and the cryobot concept, if it ever flies, would be the most extreme. Example would be required to meet bioburden standards far more stringent than those applied to missions. Landing on Mars. The hardware must be assembled in cleanroom facilities where the air is continuously filtered, where surfaces are regularly tested for microbial contamination, and where every person entering the room wears full-body protective garments that prevent skin cells, hair, and respiratory droplets from falling onto spacecraft components. After assembly, many components are sterilized using ultraviolet radiation exposure, dry heat baking at temperatures that kill resistant spores, or hydrogen peroxide vapor treatments that penetrate surfaces at a molecular level. The goal of all this effort is not to achieve a contamination level of zero that may be physically impossible for hardware assembled by biological organisms in a biological world, but to reduce the number of viable organisms on the spacecraft to a level so low that the probability of any surviving the journey and establishing themselves in a new environment approaches negligibility. For a cryobot, Those standards would need to be applied not just to the outer surface, but to every component that might come into contact with European water, which is to say every component of the vehicle. The sterilization challenge scales with the complexity of the probe. A more capable probe carrying more instruments and more mechanisms presents more surface area, more internal cavities, more potential refugia for resistant organisms, and more difficulty in verifying that sterilization has been achieved. All of this lies in the future, the medium-term future at best, the distant future at worst. Europa Clipper, currently en route to the Jovian system, carries no cryobot. It carries no lander. It will not touch Europa's surface or penetrate its ice. What it carries are instruments designed to read signals that pass through the ice from below and from above, and to gather the reconnaissance data that any future surface or subsurface mission would need before it could be designed. The 30-kilometre wall between the ocean and space remains unbroken. What it separates from the rest of the universe remains, for now, entirely unknown. But if it were possible to pass through, if some future technology solved the communication problem, the power problem, the time problem, and the contamination problem, and a probe descended into that black water, what might it find waiting there? The first principle of astrobiology, the one that underlies every serious scientific discussion of life beyond Earth, is that the only life we know how to recognize is life that resembles what we have already found. Every detector, every spectrometer, every assay carried aboard a spacecraft designed to search for biology is calibrated against the chemistry of terrestrial organisms, their amino acids, their lipid membranes, their specific ratios of carbon, isotopes, their tendency to prefer molecular structures of a particular handedness. This is not a failure of imagination. It is an honest acknowledgement of the limits of evidence-based reasoning. When scientists talk about what life in Europa's ocean might look like, they are extrapolating outward from a single data point, the 4 billion years of biological experiment conducted on this planet, in this ocean, under this sun. That single data point, however, is more informative than it might seem, because life on Earth has not remained confined to the comfortable, sunlit, moderate temperature environments where it was first recognized. Over the last half-century, biology has repeatedly discovered organisms thriving in conditions that were previously considered incompatible with life. And each such discovery has expanded the range of environments that must now be considered potentially habitable elsewhere in the solar system. Consider Deinococcus radiodurans. It is a bacterium approximately 1 to 2 micrometers in diameter, unremarkable in appearance. It was first isolated from canned meat that had been exposed to radiation, intended to sterilize it. The meat spoiled anyway, and the organism responsible survived a dose of radiation more than 1,500 times greater than the lethal dose for a human being. It achieves this through an extraordinarily efficient DNA repair mechanism that can reassemble a genome shattered into hundreds of fragments by ionizing radiation, reconstructing the correct sequence from overlapping pieces within hours. Guinness World Records has designated it the world's most radiation-resistant organism. Its existence is a direct refutation of the assumption that the radiation environment around Jupiter, intense enough to damage spacecraft electronics, would necessarily be lethal to any life that might have originated on or near Europa. Life that evolved in such an environment over billions of years might have developed protection mechanisms that make Deinococcus radiodurans look vulnerable by comparison. Consider also the bacteria recovered from Lake Vostok. The lake sits beneath 3.7 kilometers of Antarctic ice, completely isolated from the atmosphere, from sunlight, from surface chemistry. Scientists estimate it has been sealed beneath that ice for somewhere between 15 million and 30 million years. When Russian drills finally accessed the lake in 2012, samples brought to the surface contained viable microbial DNA representing hundreds of distinct species, many of them unknown to science. These organisms had survived, metabolized, and evolved in conditions of near-total darkness, crushing pressure, extreme cold, and complete isolation from the surface biosphere for longer than the genus Homo has existed. If life can do that beneath Antarctic ice on Earth, it can survive beneath ice on Europa. The most scientifically defensible scenario for life in Europa's ocean starts at the bottom, at the boundary between the liquid water and the rock and metal beneath it. If Europa has hydrothermal vents driven by tidal heating, as many planetary scientists believe it does, then the chemical environment at that boundary is one that life on Earth has already demonstrated it can exploit. In 1977, the submersible Alvin descended to the floor of the Pacific Ocean near the Galapagos Rift and discovered something that permanently altered the boundary conditions of biology. Entire ecosystems, shrimp, crabs, tube worms, reaching 2 meters in, length-dense mats of bacteria thriving around vents that pumped superheated, chemically rich water into the cold darkness of the deep ocean. None of these organisms used photosynthesis. They were powered entirely by chemosynthesis, the extraction of chemical energy from reactions between hydrogen, sulfide, methane, and other compounds released by the vents and the oxygen, dissolved in the surrounding water. No sunlight required, no connection to the surface, just heat, water, and chemistry. In Europa's ocean, the chemical equation would be different in its specifics, but potentially similar in its fundamentals. The tidal heating that keeps Europa's interior warm also drives geological activity at the ocean floor. That activity interacting with the water above it would produce chemical gradients, differences in concentration and redox state that represent exactly the kind of energy source that chemosynthetic life exploits. The absence of sunlight, which initially seems like a fatal objection to the possibility of Europan life, is no objection at all if life there never needed sunlight in the first place. The microbial scenario, single-celled organisms metabolizing compounds at hydrothermal vents, represents the scientifically conservative end of the possibility space. It is also the most likely in the sense that microbial life requires less evolutionary time, less ecological complexity, and less energy flux than more complex organisms. A minority of scientists, however, have argued that the conservative scenario does not exhaust what is possible given Europa's specific history. Europa's ocean has existed according to current models for much of the Moon's 4.5 billion year history. 4.5 billion years is approximately the same length of time life has existed on Earth. Enough time on this planet to travel from the first self-replicating molecules to every complex organism that has ever lived. If Europa's ocean has been continuously liquid, continuously energized by tidal heating, and continuously supplied with the chemical building blocks of biology for a comparable period, the argument runs, then there has been enough time for evolution to do more than produce microbes. The researchers who make this argument are careful to specify what they mean. They are not proposing intelligent life or even anything resembling animal life as it is typically understood. They are suggesting the possibility of multicellular organisms, something like jellyfish or marine worms, or filter-feeding creatures anchored near chemical vents that would represent a more complex tier of biological organization than single-celled life, but would require no cognitive sophistication whatsoever. This remains an unconfirmed and contested hypothesis. It is not the scientific mainstream, but it is also not dismissed as impossible by everyone working in the field. The question worth sitting with before moving on to the consequences is what it would mean if any of this were true, not just for the science, but for the larger picture. If life evolved in Europa's ocean, independently of life on Earth, if the chemistry of that ocean, in complete isolation from everything that happened on this planet, crossed the threshold from complex molecules to self-replicating, organisms through its own path on its own timeline using mechanisms that may not even resemble the DNA-based machinery that underlies all life as we know it, then the implications extend far beyond Europa itself. Two independent origins of life in a single solar system, in a system that contains hundreds of billions of solar systems, changes the calculation about how common life is in the universe from an open question to something approaching a certainty. And that certainty, as it turns out, is not entirely reassuring. Because if life is common, if it arises wherever the conditions are adequate in frozen oceans beneath the ice of moons, orbiting gas giants as readily as it arises in warm shallow seas under a young sun, then the silence of the universe becomes harder to explain, not easier. A universe full of life should eventually produce life that communicates. A universe that has been producing life for billions of years in conditions far more common than Earth-like conditions should statistically be full of signals, and yet we hear nothing. The evidence is on the table, the missions are flying, the instruments are calibrated. What remains is the hardest part, facing what it actually means if we find something, or if despite everything we find nothing at all. The announcement, when it comes, will not come quickly. This is the first thing to understand about how the discovery of extraterrestrial life would actually unfold, as opposed to how it tends to unfold in films and television, where a scientist peers through an eyepiece or reads a printout and immediately reaches for a telephone to call the president. The real process would be slower, more careful, and considerably less dramatic in its moment-to-moment texture, even as it constituted the most consequential scientific event in the history of the species. A signal detected in a plume sample during one of Europa Clipper's flybys, an anomalous pattern of organic compounds, a combination of molecules statistically improbable without biological catalysis, a structural signature that chemistry alone struggles to produce, would first be flagged by automated systems aboard the spacecraft, then transmitted across 600 million kilometers of space to receiving stations on Earth where it would be downloaded, archived, and assigned to a team of scientists for initial analysis. That team would spend weeks or months ruling out instrumental artifacts, calibration errors, contamination introduced during manufacturing, and every mundane alternative explanation that experience and training could generate. If the signal survived that first review, it would be passed to a second independent team with no knowledge of the first team's conclusions, who would conduct their own analysis from raw data. If both teams reached similar conclusions, the finding would be prepared for peer review, the formal process by which scientific claims are evaluated by other experts in the field before publication. That process for a claim of this magnitude would likely involve reviewers drawn from every relevant discipline, operating under conditions of unusual scrutiny and unusual caution. The total time from initial detection to formal public announcement could be measured not in days or weeks, but in years. There is a specific historical reason for this caution, and it is recent enough that everyone involved in the search for extraterrestrial life carries it as a cautionary reference. In August of 1996, NASA held a press conference at which scientists announced that a meteorite designated ALH 84001, a rock approximately the size of a potato, recovered from the Allen Hills region of Antarctica in 1984 and identified through isotopic analysis as having originated on Mars, appeared to contain evidence of ancient microbial life. The evidence came in several forms: complex organic molecules called polycyclic aromatic hydrocarbons, present in concentrations that seemed elevated compared to contamination from Earth; carbonate globules whose morphology suggested biological precipitation; and most striking, visually microscopic structures that resembled the fossilized remains of bacteria tubular and segmented in ways that seemed to echo the shapes of living organisms. President Bill Clinton made a public statement from the South Lawn of the White House. The story led every major news broadcast in the world. For a period of approximately 48 hours, the possibility that humanity was not alone in the universe moved from the domain of speculation to something that felt to many people like confirmed fact. It was not confirmed fact. In the years that followed, each piece of evidence from ALH 84001 was contested, re-examined, and ultimately found insufficient. The polycyclic aromatic hydrocarbons were present, but at concentrations consistent with contamination from the Antarctic ice, in which the meteorite had rested for 13,000 years. The carbonate globules could be explained by high-temperature chemical processes that required no biology. The microscopic structures that resembled bacteria were real, but they were roughly 100 times smaller than the smallest known bacteria on Earth, so small that it became unclear whether they could physically contain the molecular machinery necessary for life. The scientific community never reached consensus that ALH 84001 contained evidence of life. The initial announcement, made in good faith by scientists who believed their evidence was compelling, became instead a lesson in how powerfully the desire to find life can shape the interpretation of ambiguous data, and how extraordinarily high the evidentiary standard must be before a claim of extraterrestrial life can be considered credible. The lesson is not that scientists should be timid or that positive findings should be suppressed. The lesson is that the burden of proof for the most extraordinary claim in the history of science is itself extraordinary, and that the institutional processes designed to meet that burden, independent replication, peer review extended, analysis, adversarial scrutiny, exist precisely because the consequences of being wrong are so severe. A false positive announcement of life on Europa would damage public trust in science, distort the allocation of research funding for a generation, and make the eventual announcement of a genuine discovery harder to communicate credibly. The caution is not cowardice. It is the appropriate response to the weight of what is being claimed. When the announcement does eventually come, if it comes, the immediate public response will be, to put it plainly, somewhat chaotic. Every major social media platform will experience load volumes it has never previously encountered. Every television channel with a news division will run continuous coverage. Every person who has ever thought seriously about the question of whether humanity is alone in the universe will experience some version of the cognitive shift that comes when a question held open for a lifetime is suddenly irrevocably answered, and somewhere in that flood of responses, alongside the genuine wonder and the serious philosophical reckoning and the measured scientific commentary, at least 1 million people will ask with complete sincerity whether the bacterium living under 30 kilometers of ice at the bottom of an ocean 600 million kilometers away is dangerous. Talk show hosts who have never previously expressed interest in astrobiology will invite astronomers onto their programs. Opinion columnists who specialize in politics and culture will write pieces about what this means for religion, for philosophy, for the economy, for the upcoming election. The discovery will be processed through every available cultural lens simultaneously, most of them inadequate to the task, and the result will be noise of a particular kind, genuine human, entirely predictable noise that will take months or years to settle into something resembling collective understanding. Beneath all of that noise, however, something real will have shifted. The philosophical implications of an independent origin of life within our own solar system are not subtle, and they do not require advanced mathematics to grasp. If life arose on Europa, if chemistry crossed the threshold to biology in an ocean beneath the ice of a moon orbiting Jupiter, using different chemistry, following a different path, producing organisms that share no common ancestor with anything that has ever lived on Earth, then life arose twice in a single solar system. The solar system contains 1 star, 8 planets, more than 200 known moons, and a vast population of smaller bodies. A galaxy contains hundreds of billions of star systems. If life arose twice in ours, the statistical inference about other star systems is not that life might be common. It is that life is almost certainly common, that it arises wherever the conditions are adequate, that the threshold from chemistry to biology is lower than the universe's long silence had led many scientists to suspect, and that the billions of planets and moons in the galaxy with liquid water and chemical energy sources are not empty. This changes the question. It does not answer the question, it changes it. The question is no longer whether life exists beyond Earth. The question becomes why, given that life appears to be widespread, the universe is so thoroughly, so persistently, so eerily quiet. But finding life is only half of the problem. The other half is this: what do we do next? Imagine a sample return mission. A spacecraft descends to Europa's surface, deploys a probe that penetrates the ice, collects a sealed canister of ocean water containing whatever is living in it, and returns that canister to Earth. It is the logical next step after detection, the step that would allow biologists to study Europan organisms directly to sequence whatever passes for their genetic material, to understand their biochemistry in the kind of granular detail that remote sensing from a flyby spacecraft can never provide. It is the step that would transform the discovery from a confirmed fact into a comprehensively understood fact, and it may be the most dangerous thing humanity has ever seriously considered doing. The danger runs in both directions simultaneously, and each direction is serious in its own right. The forward direction, the contamination of Europa's ocean with terrestrial microorganisms, has already been discussed in the context of what engineers must prevent when designing any probe that might contact Europan water. But the reverse direction, bringing Europan material back to Earth, introduces a category of risk that forward contamination does not. Terrestrial bacteria introduced to Europa's ocean would encounter an environment shaped by 4.5 billion years of Jovian tidal forces, deep cold crushing pressure, and whatever chemistry the ocean's geology produces. Many of those bacteria would die. Some might survive and reproduce. The outcome would be uncertain and potentially damaging to Europan life. But the damage would be contained within Europa's ocean, an enclosed system separated from Earth's biosphere by 600 million kilometers of vacuum. Europan organisms brought to Earth would arrive in an environment whose biosphere has had no prior exposure to them, and no evolutionary history of defending against them. The human immune system and the immune systems of every other organism on this planet developed through 4 billion years of coevolution with the specific pathogens, parasites, and competitors that exist on Earth. That coevolution produced defenses calibrated to Earth's biology defenses that recognize certain molecular patterns as foreign and respond to them appropriately. A Europan microorganism, if it exists, would have been shaped by an entirely different evolutionary history, producing molecular structures that Earth's immune systems have never encountered and may not recognize as threats requiring a response. The immune system's failure to recognize a pathogen is not a theoretical concern. It is the mechanism underlying some of the most devastating disease events in human history. This is not a prediction that Europan microorganisms would be harmful to Earth life. There is no scientific basis for that prediction, because there is no scientific basis for any prediction about the properties of life that has never been observed. It is a statement about uncertainty. The consequence of being wrong about the harmlessness of a returned sample in this case is not a failed experiment or a retracted paper. The consequence could be an infectious event for which no defense exists, and no treatment can be developed quickly enough to matter. The precautionary logic that applies here is the same logic that underlies biosafety level 4 containment for the most dangerous known pathogens on Earth. The recognition that when the potential downside is irreversible, civilization scale caution proportionate to that downside is rational, not paranoid. The international body responsible for establishing standards around exactly this problem is the Committee on Space Research, known by its French acronym COSPAR, which operates under the International Science Council and advises space agencies worldwide on planetary protection policy. COSPAR's planetary protection guidelines assign every mission a category based on the probability of contamination and the scientific interest of the target body. Category 1. Missions flybys of bodies with no scientific interest from a contamination perspective have essentially no restrictions. Category 5. The highest level of concern applies to missions that return samples from bodies with the potential to harbour life that could be hazardous if brought back to Earth. Europa is a Category 5 target. So is Mars. So is Enceladus, the moon of Saturn that sprays water vapour from a subsurface ocean through cracks in its south polar ice. Any mission that lands on Europa contacts its ocean, and returns to Earth falls under the most stringent sterilisation and containment requirements in COSPAR's framework requirements that include not just the sterilisation of outgoing hardware, but the containment of returned samples in facilities that prevent any possible exchange between the sample and Earth's environment until the sample has been thoroughly analysed and declared safe or destroyed. The practical infrastructure for receiving housing and analysing a returned sample from a Category 5 body in the way COSPAR's guidelines would require does not currently exist anywhere on Earth. Building it would be a scientific and engineering project comparable in complexity and cost to the mission that collected the sample in the first place. Behind the technical and regulatory framework, however, lies a question that no existing international agreement fully addresses. Who decides whether to attempt contact with Europa's ocean at all, and on what basis? The Outer Space Treaty of 1967, the foundational document of international space law, establishes that no nation may claim sovereignty over any celestial body, that space exploration shall be conducted for the benefit of all countries, and that states are responsible for the activities of their nationals in space. It does not address the possibility that a celestial body might harbour its own indigenous life. It was written in a moment when the discovery of extraterrestrial biology was theoretical rather than imminent, and its framers did not attempt to specify what obligations humanity might have toward life discovered elsewhere in the solar system. The treaty is silent on whether the interests of indigenous Europan microorganisms, if such organisms exist, impose any constraint on what humans may do to the ocean those organisms inhabit. The gap in the legal framework reflects a gap in the ethical framework. The history of contact between technologically advanced civilizations and less technologically capable ones on Earth offers precedents that are instructive without being comforting. When European explorers arrived in the Americas in the late 15th century, they carried with them microbial passengers, smallpox, measles, influenza, diseases endemic to European populations that had developed partial immunity through centuries of exposure that proved catastrophically lethal to indigenous populations with no prior contact and therefore no acquired immunity. Estimates of indigenous population decline in the Americas in the century following first contact range from 50 to 90%, with the majority of deaths attributable to infectious disease rather than direct violence. When Polynesian navigators reached previously uninhabited Pacific islands, and later when European sailors followed them, the pattern repeated wherever populations met across an immunity gap. The technologically superior party was not in most of these cases the biologically vulnerable one. Europa may represent an inversion of that pattern. Humans arriving at Europa in this scenario are the technologically capable party, the ones with spacecraft and drills and sample canisters. But the microbial world we carry with us, invisible and involuntary, may be precisely the vector through which harm flows to whatever is living in that ocean. We would be in this scenario inadvertent conquerors not through malice or indifference, but through the simple biological fact of being alive and unable to leave our microbiome behind. Some scientists working at the intersection of astrobiology and ethics have begun arguing that before any mission capable of contacting Europa's ocean is designed, funded or launched, humanity needs something that currently does not exist: a formal international consensus on the ethical framework governing contact with extraterrestrial life. Not a technical protocol for sterilization. Those protocols exist and are continuously refined. A moral framework. A document that attempts to articulate what obligations the discovery of life beyond Earth would impose on the civilization that made the discovery. A kind of charter for extraterrestrial life, negotiated among nations and scientific communities, and in some proposals representatives of broader civil society, that would establish principles for how to proceed or whether to proceed once the ocean is no longer hypothetical and its inhabitants are no longer theoretical. No such charter exists. No formal international process for creating one has been initiated. The question of what we owe to life on other worlds is at the moment answered only by the planetary protection guidelines of individual space agencies operating under a 60-year-old treaty that never anticipated the situation. It may soon be asked to govern. And if we look further than the technical and legal questions, if we step back from the engineering and the policy and the biosafety protocols and ask what Europa is really telling us about ourselves, then the moon becomes something more than a scientific target. It becomes a mirror, and what it reflects back is not just the question of whether life exists out there, but the question of what kind of civilization we are and whether we are ready for the answer. The universe contains approximately 400 billion stars in the Milky Way alone. Not 400 million, 400 billion. The number is so large that it resists genuine comprehension. If you counted one star per second without stopping, you would need more than 12,000 years to finish. The majority of those stars host planetary systems. A substantial fraction of those systems contain planets or moons situated at distances from their host star, where liquid water could, under the right conditions, exist. The numbers cascade outward into something that should, by any reasonable probabilistic accounting, produce an overwhelming abundance of life throughout the galaxy. Now consider a more conservative version of the estimate. Suppose that only 1 in 1,000 star systems produces a planet with the right conditions for life. Suppose that only 1 in 1,000 of those planets actually develops life. Suppose that only 1 in 1,000 of those living worlds eventually produces a civilization capable of detectable communication across interstellar distances. Run those numbers against 400 billion stars, and you still arrive at 400 civilizations in the Milky Way alone. Civilizations that should, if they have been around long enough, have had time to signal their existence to expand, or at minimum to leave some trace that a sufficiently attentive receiver could detect. The galaxy, by this accounting, should be loud with the signatures of intelligence. It is not. The galaxy is silent. Every radio telescope array humanity has pointed at the sky has returned the same answer: nothing. Unambiguously artificial, nothing that could not be explained by natural astrophysical processes, nothing that carries the unmistakable signature of a mind behind it. The search for extraterrestrial intelligence has been running in various forms for more than 60 years, scanning billions of radio frequencies and optical channels. and the result is a silence so complete that it has acquired its own name. The Fermi paradox, named for the physicist Enrico Fermi, who is said to have posed the essential question over lunch in 1950: if the universe is so large and so old, where is everybody? The paradox is not merely an absence of evidence, it is the mismatch between what the numbers predict and what observation confirms. If the numbers are right, the absence of detection is itself a data point, one that demands explanation. Europa sharpens this paradox in a way that should be deeply uncomfortable. Before Europa, the working assumption underlying most estimates of the prevalence of life in the universe was that liquid water required a fairly narrow set of conditions to exist. A planet needed to orbit its star at the right distance, not too close to boil, not too far to freeze. A region astronomers call the habitable zone, or with the kind of understated optimism that characterizes the field, the Goldilocks zone. Earth sits comfortably in the Sun's habitable zone. Mars sits near the outer edge. Venus sits inside the inner boundary, its surface hot enough to melt lead. The habitable zone framework implied that life-bearing worlds would be relatively rare planets, with exactly the right orbital distance, exactly the right atmospheric composition, exactly the right combination of circumstances to maintain liquid water at the surface. Europa invalidates this framework, or at minimum forces a dramatic revision of it. Europa does not orbit the Sun in the habitable zone. Europa orbits Jupiter, which orbits the Sun at a distance of approximately 778 million kilometers, more than 5 times Earth's orbital distance. At that distance, the Sun is a bright star, not a furnace. The surface of Europa receives so little solar energy that it is frozen to roughly minus 160 degrees Celsius. By the habitable zone framework, Europa is nowhere near the region where life should be possible. And yet, by every line of evidence currently available, it harbours a liquid ocean larger than all of Earth's oceans combined, maintained not by solar energy, but by the gravitational kneading of Jupiter's tidal forces. The implication is not subtle. If liquid water can exist and persist for billions of years in a place as far from the Sun as Europa, then the habitable zone is not the only place where life could arise. The subsurface oceans of icy moons are environments that can maintain liquid water independently of their star's warmth, powered instead by tidal heating or radiogenic heat from decaying elements in a rocky core. Estimates suggest that there are more such subsurface ocean worlds in the outer solar system alone than there are planets in the Sun's traditional habitable zone. Scale that finding to the rest of the galaxy and the number of potential life-bearing environments expands by orders of magnitude. If the barrier to the origin of life is lower than the habitable zone framework suggested, if life can begin not just on warm sunlit planets, but also in cold, dark, ice-sealed oceans warmed by tidal friction, then the number of worlds where life might have started is vastly larger than previously assumed. And if the number of worlds where life might have started is vastly larger, the Fermi paradox becomes correspondingly more severe. The silence is harder to explain when the universe has more opportunities to produce the thing that is supposed to be filling it with noise. This is the point at which the Fermi paradox intersects with a theoretical framework proposed in 1998 by the economist Robin Hanson, a framework that has since become one of the most discussed and most unsettling ideas in the science of life's cosmic distribution. Hanson called it the Great Filter. The Great Filter begins with the same observation as the Fermi paradox. The universe appears empty of the detectable signatures of advanced civilizations despite the mathematical expectation that it should be full of them. Hanson's contribution was to frame this observation as a constraint on evolutionary history. If the universe is not full of advanced civilizations, then somewhere along the path from simple chemistry to a civilization capable of interstellar communication, something stops almost everything. There is a filter, a bottleneck so severe that virtually no lineage passes through it. The filter might represent the difficulty of forming the right kind of star. It might represent the difficulty of life originating at all. It might represent the difficulty of single-celled life developing into complex multicellular organisms. It might represent the difficulty of intelligence arising from complex life. Or it might represent something that comes after intelligence, some barrier or trap or catastrophe that terminates advanced civilizations before they leave a lasting signature. The question that matters, the question that keeps some researchers awake at night, is not whether the Great Filter exists. The silence of the universe is strong evidence that something like it does. The question is where the filter sits relative to us. If the filter lies behind us, if it corresponds to one of the early steps on the path that Earth's life has already taken, then we are the lucky exception. Life originating from chemistry might be extraordinarily improbable. The jump from single-celled to multicellular life might require a set of circumstances that almost never occurs. The emergence of intelligence from biological complexity might be a near miracle. On this reading, the Milky Way may be full of worlds with simple microbial life and nearly empty of worlds that have progressed beyond it. Humanity would sit on the far side of the filter, in the rare category of civilizations that made it through looking back at a galaxy of failed attempts. If the filter lies ahead of us, if the steps we have already taken are not especially improbable, but something catastrophic awaits civilizations at a later stage, then the silence of the universe is a warning about our own future rather than a record of our past good fortune. Civilizations routinely arise. They develop technology, and then at some stage that we have not yet reached, something destroys them. Whether through the weapons their technology enables, through the environmental damage their industry causes, through the artificial intelligences they create, or through something we have not yet imagined, the galaxy would be full of the ashes of predecessors who reached approximately where we are now and did not survive the transition. Europa is a key to determining which of these readings is closer to the truth. If Europa's ocean is sterile, if the most habitable non-terrestrial environment in the solar system, one that has existed for billions of years with liquid water and an energy source and the chemical ingredients that life on Earth uses, if even that environment produced nothing, then the origin of life is almost certainly the location of the Great Filter. Life may be extraordinarily improbable, a cosmic accident that happened once and has not been repeated in any environment we can examine. That would be deeply humbling, but in a strange way, it would also be reassuring. It would mean that the filter is behind us, that humanity is on the far side of the bottleneck, that our future is not already foreclosed by a pattern that has ended every civilization before us. If Europa's ocean contains life, if the biologists and astrobiologists who have spent careers building the case for Europa's habitability turn out to be right, and the first data from Europa Clipper or a subsequent lander reveals the molecular signatures of biology, then the origin of life is not the filter. Life arises wherever the conditions are adequate. It arises in sunlit oceans on terrestrial planets. It arises under ice on frozen moons in the outer solar system. It is not rare. It is the expected outcome of chemistry given sufficient time and the right materials. And in that case, the Great Filter, the thing that is keeping the galaxy silent despite being full of living worlds, almost certainly lies ahead of us, at our stage of development, or somewhere between our stage and the stars. The discovery of life on Europa would be the most important scientific finding in human history. It would also be, by the logic of the Great Filter, the most terrifying. Every congratulatory press release, every celebration of human curiosity and ingenuity, every speech about what it means for our understanding of our place in the cosmos, all of it would be delivered against the background implication that we may be looking at our own probable fate written in the biology of a frozen moon. So here is the question that this entire chain of reasoning arrives at, the question that deserves to sit with you for a moment before the answer is chased away. Do you want Europa to have life? Or, knowing what the answer implies, do you want it to be empty? There is no comfortable resolution to that question. The universe has arranged things so that the answer we hope for confirmation that we are not alone, that life is a cosmic property rather than a terrestrial accident, may be precisely the answer that predicts our termination, and the answer that would spare us that implication, a sterile Europa. An ocean with nothing in it would confirm a loneliness so profound that it reshapes the meaning of everything we have built and everything we are. After all of this, after the tidal forces and the ice and the plumes and the ethical paradoxes and the silence of the galaxy, what remains is the oldest and simplest question: what are we, and where do we stand in a universe that may be either empty or full of warnings? In 1610, Galileo Galilei pointed a telescope at Jupiter and noticed 4 points of light that moved. He tracked them night after night, and what he realized, the thing that shook the intellectual foundations of his century, was that those points of light were orbiting Jupiter, not Earth. They were moons of another planet. They were proof that Earth was not the center of everything that other worlds existed, that the universe was larger and stranger than the cosmology of his time had room for. One of those 4 points of light was Europa. Galileo saw it as a pinprick against the darkness, indistinguishable from the others, defined entirely by its motion relative to the giant planet it circled. He had no way of knowing what it was. 415 years later, we know that Pinprick contains an ocean larger than every ocean on Earth combined. We know it has existed in liquid form for potentially billions of years. We know its floor may be geologically active, producing the same kind of hydrothermal chemistry that on Earth supports entire ecosystems entirely independent of sunlight. We know its surface is young, continuously renewed by processes operating beneath it. And we know that something below that surface periodically vents material into space, as if the moon is exhaling. The distance between what Galileo saw and what we now understand is one of the most dramatic expansions of knowledge in the history of science, and it has happened entirely without anyone ever visiting the place, entirely through instruments, and mathematics, and the patient accumulation of data from spacecraft that pass by without stopping. What Europa has already taught us before any mission has penetrated its ice, before any probe has touched its ocean, is that our definitions are wrong. Every time humanity has drawn a boundary around the concept of habitability, around the set of conditions under which life could possibly exist, the universe has found a way across that boundary. Life on Earth was discovered in nuclear reactor cooling ponds in the superheated vents of deep ocean floors, in ice cores drilled from kilometers beneath the Antarctic surface in the hypersaline lakes of the Atacama Desert, where almost nothing else survives. Each discovery pushed the definition of habitable a little further into the territory that had previously been labelled impossible. Europa is that process operating at the scale of an entire world, a reminder that the word habitable has never been a description of the universe's limits. It has only ever been a description of our imagination's current reach. The creatures living around the hydrothermal vents of Earth's deep ocean floor, the tube worms extending 2 meters from their anchored bases, the ghost white crabs picking their way across mineral chimneys, the archaea metabolizing, hydrogen sulfide in water, hot enough to cook food. The creatures never knew that biologists considered their environment incompatible with life until biologists arrived in a submersible and found them already there, already ancient, already embedded in ecosystems of staggering complexity. The universe did not wait for our permission. It did not wait for our theories to catch up. It built life in the dark at pressure without light, and carried on without us for millions of years before we had the instruments to notice. The genuinely frightening possibility that Europa raises is not that something is alive beneath its ice. It is what would follow if something is alive beneath its ice, and that something turns out to be genuinely fundamentally different from everything biology has ever described. Not a variant, not a distant cousin using the same genetic alphabet in a different dialect, something built from different principles operating through different chemistry, representing a second and completely independent invention of the process we call life. Because if that is what Europa holds, then every textbook in every biology department on Earth becomes a document about one example rather than a description of a universal phenomenon. The entire architecture of modern biology, the central dogma of molecular biology, the universal genetic code, the shared biochemical pathways that link every organism from a bacterium to a blue whale, all of that would become the story of one lineage, not the story of life itself. The philosophy of life would require the same revision. Every framework that has been built around the question of what distinguishes living from non-living matter, every theory of consciousness that takes the specific architecture of Earth's nervous systems as its starting point, every ethical and religious tradition that places humanity's significance in the context of being the sole or primary bearers of complex awareness in the cosmos, all of it would need to be rebuilt on a broader foundation, not discarded but reconsidered from the beginning with a larger set of examples in view. It is the kind of revision that happens rarely in intellectual history, the kind that takes generations to fully work through, and the kind that, when it happens, does not feel like progress while it is occurring. It feels like the ground shifting. Europa Clipper is at this moment in transit. It was launched in October of 2024 aboard a SpaceX Falcon Heavy rocket, and it is currently crossing the distance between Earth and Jupiter, a journey of approximately 600 million kilometers that will take until 2030 to complete. It carries 9 scientific instruments, each designed to read a different aspect of Europa's nature. A radar system that can penetrate up to 30 kilometers of ice. A mass spectrometer, capable of analyzing the chemical composition of any plume material. It passes through a magnetometer to measure the induced magnetic field that reveals the ocean's properties, cameras and spectrometers to map the surface and identify the compounds that have migrated upward from below. It is the most sophisticated scientific payload ever sent to the outer solar system for the specific purpose of assessing another world's potential to support life. It will not land, it will not drill, it will conduct 49 close flybys of Europa, approaching as close as 25 kilometers above the surface, gathering data on each pass before retreating from Jupiter's radiation belts to protect its electronics. From those 49 encounters, the science teams will build a portrait of Europa more detailed than anything constructed from the Galileo spacecraft's 11 passes or the Hubble Space Telescope's distant observations. The portrait will not answer the question of whether life exists. It will determine whether the conditions for life are as complete as the current evidence suggests and whether a follow-on mission capable of penetrating the ice is scientifically justified. That follow-on mission, if it is designed, funded, launched and successfully executed, will be decades away. The question of whether Europa's ocean harbours life will not be answered quickly. It will be answered slowly, carefully, through the accumulation of evidence gathered across multiple missions spanning multiple generations of scientists. This is how science works when the stakes are highest and the consequences of error are most irreversible, not in a single announcement, but in the gradual convergence of independent lines of evidence toward a conclusion that can eventually bear the weight of what it means. Beneath tens of kilometers of ice in absolute darkness at pressures that would crush any vessel humans have yet built for deep-sea exploration, there may be nothing. The ocean may be sterile, its chemistry rich but lifeless, its hydrothermal vents venting into water that has never organized itself into the self-replicating energy-harvesting complexity that defines biology. That outcome would mean Europa is a remarkable place, a scientifically extraordinary place, but ultimately a place where the universe tried the conditions and did not produce the result. Or there may be something that has been swimming or drifting or anchored to a mineral chimney at the ocean floor for a period of time longer than complex life has existed on Earth. Something that has never seen light, never felt a tide that was not Jupiter's, never had any conception that a rocky sunlit world 600 million kilometers away was slowly developing the technology to come looking. Something that does not know it is being looked for. Something that will not know, even when it is found. In a few years, Europa Clipper will complete its first close approach of Europa. The instruments will begin transmitting data. The scientists waiting at their terminals will start seeing for the first time with this level of clarity what lies beneath that fractured, rust-streaked, impossibly ancient young surface. The numbers will come in slowly, requiring analysis and cross-checking and the long, painstaking work of interpretation. And somewhere in those numbers, somewhere in the radar returns and the mass spectrometer readings and the magnetic field measurements may be the first evidence tentative and requiring years of confirmation that we are not the only place in this solar system where the universe has tried to live. We will know